We have the great pleasure to have today Valentin Vielzeuf. He's currently a researcher at Orange Labs, mainly focusing on speech recognition, spoken language understanding, and complexity reduction. He holds a PhD in the field of multimodal deep learning, and he also has a background in computer vision. So without any further ado, I'll let Valentin talk about his presentation.
Thank you for the introduction. I hope you can hear me well. So I'm trying to present some research activities we have, also some production activity we had in my team. So it's the reason why I entitled this presentation Speech Recognition Toolkits in Focus, as we used several toolkits, including, of course, SpeechBrain. And I will try to provide some quick overview of different projects and what we learned from that. And you will see that there are a lot of conclusions that have answers from the previous presentation, especially on future works that will be done in the SpeechBrain toolkits. So it's a great news for us. So quick presentation of Orange, which formerly was France Télécom. And the firm is mainly working on networks, cyber defense, but also innovation and business services. And there are more than 100 employees and only 700 full-time researchers across 26 countries. And my team is mainly focusing on the half research, half production, and especially speech to text. Since 2018, even if we had historical activities on neural networks for multimedia analysis, such as my PhD, and computer vision. And the organization is such that we have 4 full-time researchers, postdocs, PhD students, but also people working on the development and data science. For example, for a speech-to-text solution for internal and external clients, and also on voice generation.
Valentin,
so basically,
sorry to interrupt,
yes.
but like people asked, could you remove like the your
Oh, sorry. Yeah, of course. I didn't see it. Is it better?
Yes, thank you.
Okay. So we use SpeechBrain for 2 different main projects, let's say for speech-to-text benchmarking and prediction, and also inside some research projects. So I will speak also about prediction, even if I'm not in the production part of the team. I had some a lot of interaction with this part of the team, of course. So what did we use in production in the decade before 2020, let's say? We used something that could fulfill client needs, and it's kind of usual. It's like what is needed is offline and streaming speech to text, and inference real time on a single CPU. So it's kind of really difficult to get with some models, and all the classic challenges to adapt to several languages and to easily adapt to new vocabulary, and without too high cost. And the current, at this time, internal solution was an hybrid approach, which was call-based with some modification, and especially a lot of work on MLOps and continuous integration to be able to be fast and to train acoustic models very fast, etc. And to let people just click to train a model, let's say. And the fact is that from the research side, we see, let's say, a rise of end-to-end approaches in research papers, especially in 2019. And the question was, how does it compare to what we were using in production, knowing client constraints? So not only in terms of order rate. And it's the reason why we did an internal benchmark with 3 different languages and several different domains, trying to investigate on the production constraint and to compare with the current production solution at this time again. So more details about the dataset that were used, mostly public corpora for English, like Tedlium, etc., and some internal corpora that were harder for English meetings with a lot of accents, some English TV that were chosen with specific vocabulary, for instance. For the French corpora, which is the main corpus, let's say, some public corpora and several hours of internal corpora that are specific to Orange with meetings, phone call, etc. And also a test was done on Wolof using public corpora and from what I understood, limited internal corpus. And what we did in the study was comparing 2 main toolkits, SpeechBrain and Nemo from NVIDIA, because in, let's say, 2020, it was the toolkit that were the main toolkit to implement several architectures, even if we tried our toolkit like ESP.NET, etc. And the main constraints we fixed was training on 4 consumer GPUs in less than 7 days and trying to achieve this CPU inference in near real time. And for that, what we wanted to do was to follow production steps and to implement all the steps both for SpeechBrain and for Nemo. We almost achieved that, but not for the text normalization part, where we use the Nemo tutorials and implementation. Yet we observed good, let's say, training compatibility and similarity between the input for Nemo and SpeechBrain, basically the same principles, even if they are really different things after that. And the conclusion of this first step was that for many things we were comparing this, let's say, the same methods, but for data augmentation, we were gaining a lot of time with SpeechBrain. And for inference, it was a former version of SpeechBrain. It was not as straightforward as with Nemo, where we just use a checkpoint and launch inference like that. One feedback from the production team at this time was that they wanted to do data creation, changing the, for example, updating the dataset annotation, etc. And they wanted to do it manually to explore and to analyze, not only in terms of water rate, but also in terms of just visualizing some errors and some specific words. And it's the reason why they modify the Nemo Speech Data Explorer, which is basically a visualization tool, such as like that, where you can see, for example, text, and you can classify the sample by, for example, water rates or whatever metrics you want, and just kind of analyze and see if there is a problem in terms of annotation or if it's a problem with the model. And you can just use it with SpeechBrain, converting the CSV, and with SpeechBrain prediction, it's clearly okay too. And what they did is something that is able to use both, and it's not public, but I hope we can release some visualization tool like that. This tool allows to, for example, review and listen to all the samples, etc. And also is integrated in the production continuous pipeline, allowing to just modify the dataset line and generate a new version, or even launch a training run directly there. So just to show what people from production in our team are waiting for. And if I come back to the results of the study, we observe something that is today pretty normal, let's say. First, on the corpus English corpus, most corpora are very clean, and so energy-based vocal activity detection was enough. It's the reason why we observed that in one technical report. And also end-to-end approaches improve water rate compared to the current production model. We have to note that it was a small hybrid model, and it does not solve the debate. What if you use something more recent, such as a key to approach, etc. And we also did some study with SpeechBrain and with NEMO on complexity, for example, to just validate the quadratic complexity according to the sequence length for approaches based on attention. And what we also observe is that we did not get the same conclusion, not exact same conclusion on French, because, for example, the vocal activity detection was not performing well because of music background extra, and it's there that approaches such as C0 or SpeechBrain vocal activity detection was really better. So we tried fine-tuning, even some vocal activity detection recipe, and had a focus on noise environment and augmentation. And in the other side, for low resource setting, we observed, of course, failures, let's say high water rates of end-to-end models when training from scratch and not fine-tuning. And SpeechBrain at this time, 1 year and a half ago, allows easy and straightforward fine-tuning of Wave 2, Wave 2. It's kind of well known, but it was really interesting because it allows to have really quick results for English, French, and Wolof, and to compare to internal solution. What I did not add to the results is that we also evaluated Whisper more recently and compared it to other approaches. What we conclude is that Whisper was interesting for our research work part and even for maybe annotation in English, but was not outputting enough confident text for the French part, especially when there was a very specific vocabulary. Maybe with fine-tuning, people will achieve something interesting. If I detail the production feedback, and I will finish for the production part, what they say is we will use NEMO for 2022 because conformer with SIP was easier to make converge. And one important thing was that it was based on PyTorch Lightning, while SpeechBrain was built in. I find it as an advantage to have it all built in, but for some people, for some user of PyTorch Lightning, it's easier to cope with, I guess. And the main focus was on visualization and analysis. Yet, in the research side, and I will explain what we do, we are using SpeechBrain, especially because also we observe good resilience and compatibility with Slurm on our HPC. And we're also, it feels like easier to modify recipes from scratch. So I will try to provide some details on that in the second part. So about research projects, the first one is about Lucas' thesis and focused on spoken language understanding. Lucas is supervised by Yannick Esteve and me. And I will provide several examples where we were using SpeechBrain and how we modify it. The first one is fine-tuning Whisper, and it has been done by probably others, but it was the first step. And adapting it to ESTOP dataset, which is a version of top dataset, but vocalized. And for example, you have to predict from a specific command, such as direction to the Eagle game, some semantic parsing which yields a hierarchical representation of semantic. And the question was, is such a model able to predict hierarchical structures? And the answer is yes. And there are several works from others also that confirm this finding. And we did not stop there, but we tried to adapt Whisper to dialogue state tracking. So basically, using the DSTC11 challenge, which proposed to vocalize the multi-voice dataset. So just a quick reminder about DST. It consists in, for example, one agent and one user having a dialogue. And for example, here you can see someone that is trying to book an hotel, and you will try to update all along the dialogue the state of the dialogue, saying that you are booking a hotel that is in the north area, etc., etc. And you just change the state if you, for example, cancel your reservation. Therefore, you need to integrate context, and it was really interesting to do it with SpeechBrain, because we just work on the data pipeline and integrate some prompts, doing the integration this way as a first time. Today we still have some problem of convergence, but the implementation is relatively straightforward with such a tool, so I guess it's worth mentioning. And we also try to implement it in another way by combining speech-to-text and natural language and understanding blocks in an end-to-end fashion, doing the gradient flows. And the modularities of SpeechBrain's allow to use instead, for example, using face models extra easily. And it's a reason why we did it with SpeechBrain. It was really, it would have been really difficult to do it otherwise, because the data pipeline is kind of complex in a framework such as Hugging Face, let's say. If you have to try really like a lot of different methods, it's what we did for the different combination. And today we have first results. Hopefully we will share in the next month about that. Another research project is Luis Martinez postdocs, which just began 2 months ago in our team, and it echoes to what Tito and Parcode presents before about efficient self-supervised, and we are just beginning to investigate it, so probably we'll try to contribute to SpeechBrain about that. And what we are trying to do is to implement the spiral approach, but with an efficient implementation, meaning the spiral approach is a, let's say, noisy student self-supervised approach for speech, and has been published in ICLR in 2021. And in the paper, they do not try to optimize, let's say, the efficiency of the training, and just basically using flash attention, trying to preserve the loss with mixed precision, compatibility, and tuning a little bit the hyperparameters. We achieve mono GPU training. Yet we are not under 48 hours, as I wrote, but we are, let's say, really faster than the original article. And right now we are trying to really be sure to be closer to the water rate obtained by the authors, etc. So fixing some problems about it. Luis is using dynamic batching from SpeechBrain features extraction, just using not exactly the same features as the article. We tried a lot of different ways to do, for example, subsampling in the features, and also we tried different data augmentation with the SpeechBrain toolkit. And recently, he adapted his implementation using the data pipeline of SpeechBrain and PyTorch Lightning. And it was relatively okay too and easy to do. And the comeback to SpeechBrain is kind of easy too. So we have two branches and it's possible to do both. And finally, some words about supervised speech-to-text in the context of efficient. One lesson we learned was with the internship of Maxime Berkeley, who is a PhD student in Germany right now. And we implemented an efficient conformer in 2020. And we tried to adapt it to Nemo and SpeechBrain, and we did not succeed for Nemo. We achieved a recipe for SpeechBrain, but we did not do a pull request because water rates were a bit far from the paper. There is an official implementation that is standalone. What we learned is that integration of such a model is kind of easier in really modular toolkits such as SpeechBrain. So it's a really important lesson for us. And probably for next project, we'll put more effort to contribute to the library. And also we worked on the wave-to-wake do from SpeechBrain and trying to achieve a faster inference doing usual approaches such as quantization, segmentation, on NX. It was for internal usage, and we also study the impact on fine-tuning of ascending and descending curriculum learning, and observe exactly the same conclusion as the SpeechBrain community, meaning that we could achieve for fine-tuning faster fine-tuning and with ascending curriculum learning on our corpora, and without degrading too much the water rate. And also we experimented, and the last one, with fine-tuning wave-to-wake too for early exiting, and it's a negative results that was never published, but I think that may be interesting for the community. Early exiting consists in saying that all the inputs are not that complex, and some input may need only one or two transformer layers, and so you may exit from the forward before the end of the inference across all the layers. And so you need to just change your network to have a classifier that yield an output for every layers of the transformer. So it was done for BERT with BERT exit first, but it could be done at this time with wave-to-wake, and it has been done for UBERT, and it's working well. It was not working for wave-to-wake 2. The fine-tuning was not converging, or even when converging, it was not yielding very good water rate results. And the community provided us an interesting explanation that was confirmed in SpeechBrain. And this explanation is that when you do some layer-wise analysis of wave-to-wake and UBERT, for example, what you see is that the similarity of the different layers, synapses, with words, meaning all laws, how good, let's say, even if it's not the case, how good the model is on a word task, you can see that the last layers are all not very good. But if you look at wave-to-wake, it looks like the best layer for speech-to-text, for instance, are in the middle, and it's what some people in the community are doing, just resetting the next layers. And that for UBERT, it's not as much the case, even if it's a little bit the case. And when doing the experiments with the same code, but with UBERT, following the original paper cited there, which is from, I guess it has been published in a conference right now, but yeah, what we observe is that indeed early exiting was working, let's say, was yielding interesting water rate results and providing acceleration. So just to share these results and to say that this study was done also with SpeechBrain, and I guess it's also a great tool for it's not production results, but it was intended to try it, for example, later in production, and it was not that difficult to implement. So it's a good way also to share it with internal manager in different companies, probably. As conclusions, Orange is using SpeechBrain for various research projects around speech. And the research code will be released in next month and years. SpeechBrain will also be studied again for some use case in production in 2024. In the other side, what we learned when working with the production part of the team is that there is a huge need for tools for having a full evaluation analysis. And I guess some of the SpeechBrain benchmarks will actually answer a part of this need. And also a need for inference pipeline. And as presented before, there is a part of what will be done in SpeechBrain that will answer that. And what was the limitation was something that was PyTorch Lightning-like, and it's a case for me in SpeechBrain. So it's just a kind of, I think, a change, and communication is something that can be challenging when evaluating the libraries, because it's kind of a subjective choice that make people choose one toolkit versus another sometimes. So just to share also that sometimes I guess making decision is not totally objective. So thank you for your attention, and if you have any questions, feel free. And also I'll let my mail. So if you want more details, because I was like providing an overview, just feel free to send a mail.
Thank you, Valentin. Thanks for the great talk. So are there any, let's see, questions from the audience? Okay. Adele asks, what do you mean exactly by available architectures?
Okay, so probably in the conclusion, what was limiting our choice when benchmarking was that SpeechBrain's was really early, and so Conformer was not converging at this time because there were some little fix to do in the implementation, and one choice that made the production go to Nemo was like there was Conformer, just plug and play and use Conformer. In the other side, it's the contrary. No, you have like, for example, Wave to Vec, easy training in SpeechBrain, or Whisper, for example. And if I'm not wrong, Whisper is not in Nemo. And I guess it's something that make people looking for off-the-shelf tools just change from one library to another. So it was just to share how this decision can be made sometimes.
All right. Thanks for the question.
Another one, right?
Sir? There's another. Yes, Mirko. And one question, you have been talking about efficient ASR. Have you tried like the latest ASR updates from SpeechBrain, like branch former?
Yes, so I did not try it right now. It's in the list. I read the paper, and I also tried other architectures such as SqueezeFormer, and I guess that the efficiency gain could be interesting, and it's probably in the plan of 2024 to validate it on internal benchmark, as it's really fast to do right now, as everything is ready for. So I guess we will definitely try it.
Yeah, Valentin, maybe feel free to get back to us when you tried maybe the branch former, some kind of competitive conformer that we now have in the new version, and hyper conformer, which I think can help a lot. But in general, let me thank you for the talk. I found it very interesting, especially because it's a kind of fair assessment about the pros and cons of SpeechBrain. Actually, you said for research it's good, but for production we need to improve something. So I just suggest maybe we can really keep in touch. At some point, maybe we will fill this gap, right, and making SpeechBrain ready for production as well. Know that we develop it for research. That's the primary purpose, but who knows? Maybe with hard working and interaction with people like you and other company, we can at some point make it production ready. There is another question, maybe if I can do it. Thanks, Valentin. I'm sorry, I may miss something. While talking about benchmarking, did you say that you managed to run inference for end-to-end models faster than Caldi in production on CPU? Thanks.
Sorry, I did not hear the question because of the sharing of the screen.
So you can read it in the chat. Essentially, it's about
Okay.
while talking about benchmarking, did you say that you managed to run inference for end-to-end faster than Caldi in production on CPU? Thanks.
Okay, so in fact, it was evaluation on for inference time is kind of tricky. What we observed is, for example, that for the Caldi solution we have is around 0.5. It's 2 times faster than real time on CPU compared to, for example, conformer small. When having the right strategy, we were able to do something like 5 times faster, but it heavily depends on how you segment and how you use your vocal activity detection. But yes, we observed that it was a bit faster with small model. But when you look for conformer large or stuff like that, or even whisper, you're far from the Caldi one, which is optimized during it's called the adapted, let's say, implementation, and it has been optimized for one CPU inference, also doing all the process with, let's say, the right implementation during years. But yes, we were kind of surprised. End-to-end models that were, let's say, reasonable, were when with the right hyperparameters were faster than Caldi ones, and we'll report some results in the technical paper that we published in arXiv in 2020.
Thank you, Valentin. I actually have one more question. At some point you said that it will be great for SpeechBrain to have an inference pipeline. So we have actually, right, some kind of easy inference
Yes.
interfaces where you can take your protein model and use it for inference. But what do you need more than that exactly?
I guess the fact is that the benchmark was done with a former SpeechBrain version. And what was very interesting, for example, with the Nemo one, was to output during the training a meta checkpoints with which is basically just a TOR file with the configuration, the PyTorch checkpoint, the tokenizer, whatever. You just put it in a archive file, and then you're able to load everything with one line of code in any over. But I guess SpeechBrain is doing it right now. I guess it was not the case in former version.
That's for training or for inference? I mean,
for inference, because what is sometimes done is you train a model and you have checkpoints that are saved. But sometimes you want to launch evaluation of, I don't know, half training checkpoints. And to perform that, it's easier if you have everything in one file. But it's basically just something that can be easily implemented in SpeechBrain. And we did the tar file with that with SpeechBrain once. So it's
okay. Maybe Yaku can comment a little bit about that on checkpointing, maybe. But I think that is feasible, right? I don't know if Aku is here and would like to share some thoughts. Yeah, I think also it is feasible, maybe.
Yes.
If Aku is here, I think he's here. He might want to say something about checkpoints. Let me see if we can.
I just gave him access.
Yeah. Maybe it's not there. But anyway, that's a great point too. Are there other questions? Looks like we are done. So what should we do, Sam? I mean, we have like a few minutes, so maybe we can.
Yeah, I think we can give a short break, right? Like until 2:30.
Okay.
That's 7 minutes basically, and then we can start.
Don't miss the last part. Don't miss the last part. It's very interesting. There will be a panel discussion.
Yes.
With many interesting people. There is Shinji here, Dan, and many others. So really, that's super cool. So maybe let's take 5 minutes break, right?
Yep.
And we see each other later. And thank you, Valentin, for your great talk. We can keep in touch and hopefully collaborate together in the future. Okay.
With pleasure.
Thank you very much.
Thank you.
5 minutes break.
5-minute break. We'll be back.